This is Dr. Sayyidin Hamza. I have got many requests from many candidates that to make a video on pressure volume loop. So this is my small effort to make the pressure volume loop easier for all of you. This is a part 1 video that will explain the basics of pressure volume loop. I hope after this video you will be able to understand the pressure volume loop and some systolic or diastolic dysfunction interpretation on pressure volume loop curves. The source is from cvphysiology.com. You can get these data from there. So starting from pressure volume loop, here is the diagram for pressure volume loop. You all are familiar with it. I'll try to make it simpler for you. Here's the cardiac cycle divided in 4 phases, the A, B, C and D. The phase D and A explains or illustrates the diastole, while the B and C illustrates the systole of cardiac cycle. I'll explain these phases in detail in the next slides. Here is shown the pressure, LV pressure curve, and here is shown the LV volume curve. The black is LV volume curve, while the red is LV pressure curve. We will explain these curves in detail in the next slides. So here is the pressure volume loop curve. The pressure is shown on the y-axis while the volume is shown on the x-axis. The horizontal deviation will be for the volume, while the vertical deviation will be for the pressure. Here the 4 shows the mitral valve opening, and the diastole starts, the LV filling starts. The 1 is for the mitral valve closing, and then the isovolumetric contraction that raises the pressure. The 2 is for the aortic valve opening. The C is for the ejection phase. The 3 is the aortic valve closing, and then the isovolumetric relaxation. This is just a brief overview. I'll be explaining these phases in detail in the next slides. I just want to show you this point is the LV and diastolic volume, and this point is the LV and systolic volume. This part shows the diastole and this part shows the systole. The difference between the end diastolic volume and the end systolic volume is the stroke volume. You just should be familiar with these terms, and we'll be explaining the pressure volume curve in detail in the later slides. So this point shows the opening of mitral valve. Mitral valve opens when the LA pressure exceeds the LV pressure. At the end of diastole, the mitral valve opens when the LA pressure exceeds the LV pressure. Then the phase A starts, which causes the LV diastolic filling. Due to this filling, the LV pressure, LV and diastolic pressure here, LV and diastolic pressure rises above the LA pressure. That causes the closure of volume mitral valve, and this shows the LV and diastole. The pressure at this point is the LV and diastolic pressure, while the volume at this point shows the LV and diastolic volume. Then the phase B starts, that shows the isovolumetric contraction. Both the mitral and aortic valves are closed at this point. Then the pressure at which the LV pressure rises above the aortic pressure, that is where the aortic valve opens. Then the phase C starts, that is the ejection phase. the blood ejects from LV to the aorta. That causes decrease in the LV volume, and the LV pressure rises because the contraction of the LV causes increased pressure in the LV, but due to ejection the volume decreases. That's why the volume curve shifts backwards horizontally. Then at this point the LV pressure decreases below the aortic pressure. That causes the closure of the aortic valve. At this point the pressure in the LV is LV systolic pressure, that is the highest pressure, and the volume is the LV end systolic volume. Then the phase D starts, that is the isovolumetric relaxation. Both the mitral and aortic valves are closed in this phase. I hope you have got an idea, a brief idea about this curve now. We will be explaining the phases now. The phase A. The phase A starts when the mitral valve opens, bottom left, when the LV pressure is lower than the LA pressure. After the end of isovolumetric relaxation, the LV pressure drops. When the pressure of LV drops below the LA pressure, when the LV pressure drops below the LA pressure, the mitral valve opens. And at the end of this phase, the mitral valve is closed. As the ventricle fills during this phase, the blood flows from LA to LV. As the ventricle fills, the LV volume correspondingly increases. I told you the volume will be represented on the horizontal axis. So the volume shifts from this point to this point. The LV volume increases. Due to this increase in the LV volume, the pressure slightly increases from this point to this point. At this point, the pressure is LV and diastolic pressure, and the volume at this point is LV and diastolic volume. As the pressure slightly increases, there is a slight slope that is called EDPBR. This is shown here. The LV pressure versus volume curve during this phase is called end diastolic pressure volume relationship, EDPBR. Normally this is like this. This slope is indicator of ventricular compliance. A more compliant ventricle will have lower pressure at higher volumes than a less compliant. An increased compliant ventricle and decreased compliant ventricular curves are shown here. The more compliant the ventricle, the shallower the slope, while a stiff ventricle will have steeper slope. For example, what it means by compliant ventricle? For example, an increased compliant ventricle at this volume, for example, this is 50 ml, this is 100 ml. At 50 ml volume, the increased compliant ventricle has, for example, 10 pressure, while the decreased compliant ventricle has 20 pressure. So the increased compliant ventricle will have lower pressure at increased volumes, while the decreased compliant ventricle will have higher pressure at decreased volume. The increased compliant ventricle will have pressure of around 20 millimeter, for example, at around 200 milliliter, but the decreased ventricular compliant ventricle will have 20 millimeter of pressure at around 75 ml. So this shows the diastolic function of the ventricle. I hope you have got that. That the increased compliant ventricular will have decreased LV and diastolic pressure at higher volumes, while decreased compliant ventricular will have higher LV and diastolic pressure at lower volume. After the end diastole, the phase B starts. That starts with closing of the mitral valve and ends with the opening of the aortic valve. This is the isovolumetric contraction phase. The LV contracts during this phase, but there is no change in the volume. So there will be no deviation horizontally as there is no change in the volume, but there will be increase in the pressure vertically as the pressure is shown on the y-axis. So the pressure rises, but there is no change in the volume. There is only change in the pressure at this point. As both the valves are closed, the squeezing action changes the aortic valve to open and blood to be ejected in the next phase, because as the pressure increases, when the pressure in the LV rises above the aorta, that causes the opening of the aortic valve. Here the isovolumetric contraction phase ends. That is the phase B. Then starts the phase C, that begins with the opening of the aortic valve and ends with the closure of the aortic valve. This is when the ejection of blood occurs. As the aortic valve opens, the blood ejects from LV to aorta. During LV ejection, the LV volume decreases. That is shown by decrease in the volume, horizontal deviation from this point to this point. The LV volume decreases from this point to this point, from LV end diastolic volume to LV end systolic volume. The LV volume decreases. This volume goes into the aorta during ejection phase. That is also shown as stroke volume. So during this ejection phase, the LV volume decreases, but the LV pressure increases due to continuous contraction of LV, and it reaches at a peak point that is called LV systolic pressure. At this point, the aortic pressure also rises because of continuous ejection of blood from LV to aorta. That causes the rise in aortic pressure. When the aortic pressure rises above the LV, that is when the aortic valve closes. That ends the ejection phase. So when the aortic valve closes, the pressure of the LV now drops. The LV and systolic pressure that can be generated at a given ionotropy. So this pressure that can be generated at a given ionotropy at a given end systolic volume is known as end systolic pressure volume relationship, ESPVR. Any of ionotropy of the LV, any systolic pressure at a given systolic volume is called end systolic pressure volume relationship. So the end systolic pressure volume relationship slope is an indicator of contractility, as the end diastolic pressure volume relationship slope was indicator of the ventricular compliance. In the same way, the ESPVR slope is an indicator of the contractility. Increased slope shows more contractility, more contractile ventricle. So this black arrow dotted line shows the normal ionotropy. When the ionotropy decreases, that shows the stroke volume decreases. So the slope of the ESPVR decreases. But as the ionotropy increases, that is shown as a red diagram, the slope of the ESPVR increases. So more steeper the slope, more contractile is the ventricle. So after the closure of aortic valve, the phase D begins with the closing of aortic valve and ends with opening of the mitral valve. During this phase, the isovolumetric relaxation occurs. And due to relaxation, there is no change in the volume, isovolumetric relaxation. So there will be no deflection horizontally. But due to relaxation, the pressure of LV decreases. That causes vertical deviation from this point to this point. As the pressure decreases, as the pressure of LV decreases, there comes a point when the LA pressure exceeds the LV pressure. That will cause the mitral valve opening, and this cycle will repeat itself. So this is the pressure volume loop. I hope you have got an insight of pressure volume loop. I'll explain it briefly again. So at this point, the mitral valve opens. That will cause the LV diastolic fill-in. That will cause the increase in the volume. I have told you the horizontal deviation is the volume. The increase in the volume of LV. That will also cause a slight change in the pressure of LV. So this slope is the diastolic pressure volume relationship slope. The steeper the slope, the less the compliance. While less steeper the slope, the more compliant is the ventricle. At this point, the LV pressure rises above the LA pressure and mitral valve closes. There starts the B phase, that is the isovolumetric contraction. Isovolumetric contraction means there is no change in the volume, but there is increase in the pressure. So the pressure rises. At this point, the LV systolic pressure is more than the aortic pressure. That will cause the aortic valve opening. As the aortic valve opens, the LV ejection occurs. The blood ejects from LV to aorta. That causes decrease in the volume of LV, but the pressure will keep rising until it reaches the maximum LV systolic pressure. At this point, the LV pressure is below the aortic pressure. That will cause the aortic valve closure. That is shown as the ESPVR slope. The steeper the slope, the more inotropic is of the ventricle is there. The shallower the slope, there is decrease in the inotropy. After the closure of aortic valve, the isovolumetric relaxation occurs. That is the phase D. There is no change in the volume, but there is change in the pressure. The pressure drops. As the pressure drops, there comes a point when the LA pressure is higher than the LV pressure. That will cause the mitral valve opening, and this cycle will continue. And the difference between the end diastolic volume and end systolic volume is the stroke volume that is ejected from LV during systole. So I hope you have got an insight about pressure volume loop, the basics of pressure volume loop. I'll be explaining the effect on pressure volume loops of preload, afterload, ventricular dysfunction, and valvular disorders in the part 2. If anyone of you still have any difficulty in understanding this pressure volume loop, you can always ask me. Thank you.